开始。
Hello, everyone. Today we are talking about the analysis of aviation safety risks and the evaluation of flight techniques. And we are from the ESAM, and my name is Haoan.
My name is Yuxiang.
I'm Zishi.
The first part of our final project is to classify the different over-limit types using K-means clustering model. There are two key goals of this algorithm. The first one is identify patterns in over-limit events, and the second one is provide insight for aviation safety analysis. Here we will briefly introduce the K-means clustering algorithm. The objective of K-means is to minimize the sum of square distance within clusters. And there are four steps. The first one is initialize K centroids randomly. Then we can assign data points to the nearest centroids. After that, we could update centroids to the mean of assigned points. Finally, we should repeat the algorithm until the algorithm converge. And the exact objective function and formulas are given here. K-means have two advantages and disadvantages. First one of advantages is simple and computationally efficient, and it is effective for large data sets. However, it is sensitive to the initialization, and it assumes spherical clusters and requires predefined K. So we will introduce the application in our exact data set, which is the over-limit events. We consider several factors, including alert level, the airplane numbers, routes, flight phases, and event names. After applying the K-means clusters, we can derive the cluster center for each cluster. And finally, we visualize the cluster results. We can see clear boundaries between clusters. To visualize the cluster result, we have to use principal component analysis to reduce the dimension into two dimensions. Conclusion is that K-means effectively classifies over-limit events, and the future work includes explore the dynamic clustering and incorporate real-time data.
The second part is evaluation of pilot flights techniques based on GBDT model. So what is GBDT model? GBDT model is gradient boosting decision tree, which is a powerful ensemble learning algorithm. It optimizes host function by fitting residuals, making it versatile for both regression and classification tasks. The model uses an adaptive approach where each tree contributes to reducing the error of the overall model. The objective of GBDT is to minimize a predefined loss function, LF, which quantifies the difference between the predict and the true values. Depending on the task, GBDT uses different loss functions. We have square error function and binary classification function and multi-class classification function. So in GBDT, gradients play a crucial role in improving predictions. At each iteration, pseudo residues are computed as gradients of the loss function. These pseudo residues represent the remaining errors after the current iteration. A decision tree is then fed to these residues, helping the model correct its predictions step by step. Finally, the model is updated by combining the predictions of the previous model and the new tree, scaled by a learning rate V, which controls the step size. So this is our data set. Our data set contains 2,368 samples, each with 197 features. The target label is landing operator qualification. It's a category grades A or C or F or J or M or T. And two irrelevant features, handling operator and TO date, were removed to focus only on flight data. The dataset was split into 80% of training and 20% of testing, ensuring a fair evaluation of the model. Next. So the experimental designing, we remove the irrelevant columns ending operator and TO date. And second, we drop the columns with over 50% missing values. Next. Uh, this is the model training progress. So we split the data into training and testing, use the GBDT as classifier within the pre-processing pipeline, and evaluated the model using classification metrics. So this is our model training result. We can find that this is a top 10 feature importance ranking in our model result. We can find that the model performs well for classes A and F, but struggles with classes C because it is inefficient samples of the class C. And top features indicate timing and flight dynamics significantly impact prediction. And overall, the accuracy of 70% demonstrated moderate predictive power.
And now we move to the third section, and we focus on the real-time warning for flight over limit events using the random forest model. And as we know, the rapid growth of the civil aviation industry has brought the new challenge to flight safety. Traditional warning methods heavily rely on the human judgment or post-incident data analysis. And these approaches are prone to human error and lack the real-time capabilities. And our study combines the QAR data with the FSM modeling to propose a new method for real-time prediction and early warning. And now we are talking about the research objectives. And let's look at the core objectives of this research. And there are three main goals. And first of all, we need to construct a state queue based on FSM to enable real-time monitoring of aircraft status. And secondly, we need to extract critical information from QAR data to support the prediction of over-limit events. And finally, we need to validate the effectiveness of the warning mechanism using the random forest model. And this slide illustrates the unique contributions of our research. And to improve the data quality, we designed a data cleaning method based on the coefficient of the variation, which is the CV, and which effectively identifies and removes the anomalies. And we also proposed a new QAR data acquisition approach that integrates the time delay constant tau and FSM modeling to build a reliable state queue. And finally, we introduced a prediction model for over-limit events based on the QAR state queue. And now we talk about the method overview. And let's take a look at the overall process of our method, and which consists of 5 steps. And first of all, we need to extracting the flight-related data from the flight records. And then we need to use the FSM to construct a state queue. And the next, we need to extracting the key features like the altitude, angles, and accelerations. And next, we need to use the random forest model for prediction. And finally, we evaluating the model's performance using the experimental data. And this slide focus on the QAR data modeling. And the QAR data records flight states every second, and including the parameters such as altitude and pitch attitude. And to construct a real-time state queue, we used a sliding window mechanism to capture the dynamic changes over a specific time frame. And we also introduced the time delay constant tau, and which reflects the aircraft's uh, inertia and the control characteristics. And by using this approach, and the state queue not only describes the current flight status, but also reflects the trends and transitions. And you can see this graph, and this graph illustrates a sliding window example. And as the window moves, it includes the data from the multiple time points, and which are converted into a state queue using the FSM and subsequently fed into the prediction model. And for each flight parameter, and we set the safety thresholds, and such as the upper and the lower limits for G values. And when a parameter approaches or exceeds its threshold, it triggers a potential event prediction. And for instance, an G value existence during the landing may result from the improper release of the control stick. And by combining the historical data and the extracted features, and our model not only detects over limit events, but also predicts the risks a few seconds in advance, and giving pilots a critical reaction time, right? And now you can see the feature extraction, and we identify the multiple features from the state queue, such as the pitch attitude and roll attitude and acceleration. And these features are highly correlated with the flight risks and from the basis of our model's prediction. And the random forest model use these features to generate the prediction. And for example, it can predict whether an over limit event will occur within the next 5 seconds. And this short-term prediction significantly enhance flight safety. And you can see this graph. And this graph shows that the distribution of the features and the logic of the model's prediction. And post feature extraction, and the data is split into the training and the testing sets. And the model leverages this data for training and validation. And I will tell you the random forest algorithm. And the random forest is a very primary algorithm we used. And it builds the multiple decision trees and use a voting mechanism to generate the final prediction. And it can enhance, includes dealing with high dimensional data and being robust to outliers in individual features. And this formula you can see, which shows the voting process. And each decision tree predicts a category based on the input data, and the final result is determined by the majority voting. And this enhances the model stability. And to enhance the model performance, and we contracted data cleaning and dimensionality reduction. And firstly, we identified and removed the invalid values, such as magnetic headings, outside the predetermined range. And then to reduce the computational complexity, we ignored the irrelevant fields. And we also used the CV to detect the anomalies. And by ensuring high quality input data, and we improved the reliability of our model. Okay, and then I will tell you our experimental results. and the random forest model achieves an accuracy of about the 87% and the F1 score of the about the 83% on the test set. And further analysis using the confusion, the matrix, and the ROC curve validated the model's prediction capabilities. And this results demonstrates that the random forest model performs well for over-limit event prediction and meets the demands of the real-time warning systems. Okay, and our model shows significant advantages in terms of the generalization capability and feature interpretability. And compared to the deep learning, the random forest model requires less computational resources and making it highly suitable for embedded system. And additionally, analyzing the feature importance provides valuable insights into which parameters contribute the most to prediction and offering a clear direction for future optimization. Okay. Okay, and finally, we summarize our project. And first of all, proposing a real-time early warning mechanism for aviation safety based on FSM and random forest. And then we verify the value of QAR data in real-time prediction. And finally, we achieve the efficient early warning with low computational resources. Okay, that's all. Thank you for listening.